Gravity is the invisible sculptor of life. It determines the thickness of your bones, the pressure in your arteries, and the very limit of how tall a tree or a civilization can grow. On Earth, we exist in a delicate Goldilocks zone of 9.8 meters per second squared. We assume this is normal, but the universe suggests otherwise.
Since the launch of the Kepler Space Telescope in 2009, we have confirmed thousands of exoplanets. A significant portion are super-Earths, rocky worlds like Kepler 452b or LHS 1140b, with masses up to 10 times that of our home. If the dice of evolution had been rolled on a world with double or triple Earth's gravity, the human blueprint would need to be radically rewritten.
To understand high-gravity biology, we must first confront the square-cube law, articulated by Galileo Galilei in 1638. It states that as an object scales up in size, its volume, and thus its mass, cubes, while its surface area only squares. But on a high-gravity world, we aren't increasing the size, we are increasing the weight for the same volume. The structural load on biological materials skyrockets.
If you were instantly transported to a 3G world, 3 times Earth's gravity, you would weigh as much as an NFL linebacker carrying 2 other linebackers on his shoulders. Your current skeleton would likely fracture under the dynamic load of a simple walking stride. Evolution, therefore, would prioritize cross-sectional area. The gracile human femur would be replaced by thick, pillar-like stanchions.
Height becomes a liability. The torque applied to joints increases with the length of the lever arm, your limbs. A high-G human would likely be drastically shorter, perhaps 3 to 4 feet tall. Imagine a morphology resembling a fantasy dwarf, but exaggerated. Massive ankles, a lower center of gravity, and a skeletal density comparable to biological concrete.
The real killer, however, isn't broken bones, it's fluid dynamics. Your heart fights gravity to pump blood to your brain. On a 3G world, the hydrostatic pressure required to overcome the vertical distance from the heart to the head would need to be immense. To prevent blood from pooling in the legs, causing immediate unconsciousness, biology would demand a radical solution.
We might see the emergence of auxiliary hearts or a distributed pumping system, similar to the venous pumps in giraffe legs, but systemic. The distance between the heart and brain would minimize, resulting in a distinct lack of neck. This prevents the siphon effect failure. Furthermore, blood pressure would be high enough to rupture terrestrial arteries, necessitating thicker, reinforced vascular walls.
Locomotion changes the game. On Earth, walking is a process of controlled falling. In high gravity, falling is fatal. The acceleration is too rapid for standard reflex arcs to catch you. Bipedalism, balancing a high mass on 2 small pivot points, is evolutionarily risky. It is highly probable that high-gravity intelligence would retain a hexapedal or quadrupedal stance for stability.
The environment itself would suppress verticality. High gravity implies a steeper atmospheric pressure gradient. The air at surface level would be incredibly dense, perhaps resembling a liquid soup. While this makes breathing easier in terms of oxygen availability, the drag on movement would be significant. You would be wading through the air, not just walking through it.
Paradoxically, flight might be easier for smaller creatures. The Archimedes principle applies. A denser atmosphere provides greater buoyancy. We might see evolution converge on sky whales, organisms using gas bladders to float in the heavy air, navigating like submarines rather than gliders. However, for a human-sized entity, the energy cost to lift mass against 3G would be metabolic suicide.
Civilization would mirror biology. The skyscraper is a monument to Earth's forgiving gravity. On a super-Earth, architecture would be subterranean or pyramidal, distributing weight over vast footprints. Stairs would be non-existent, replaced by shallow ramps. The very concept of up would be culturally associated with extreme effort and danger.
But the most profound consequence is the gravity prison. We live in a universe governed by the Tsiolkovsky rocket equation. It dictates that to reach orbit, a rocket must carry fuel to lift its payload, plus fuel to lift the fuel. The relationship is exponential. On Earth, we are barely on the edge of chemical rocketry being viable.
If Earth's diameter were just 50% larger, the fuel required to reach orbit would exceed the mass of the entire rocket. Chemical propulsion becomes physically impossible. A civilization on a super-Earth could develop computers, nuclear power, and the internet, yet remain forever bound to their planet. They would gaze at the stars with perfect telescopes, knowing they can never sail among them.
To escape, they would need to bypass chemical combustion entirely. Their first foray into space wouldn't be a gentle Sputnik, but likely a brute force nuclear pulse engine, literally detonating atomic bombs behind a spacecraft to ride the shockwaves. Space exploration would not be a scientific curiosity. It would be an act of desperate, violent engineering.
This thought experiment reveals the anthropic principle in action. We look the way we do not because it is the best design, but because it is the only design that works here. Our height, our heart rate, the fragility of our bones, they are all calibrated to the specific mass of this rock we cling to. In the cosmic lottery, we drew a ticket that allowed us to stand tall, to walk on two legs, and eventually to leave. On a heavier world, we might have been stronger, denser, and more resilient, but we would likely still be looking up, prisoners of our own weight, dreaming of a lightness we could never know.